Okay, I don't know if I'm connected. Says I'm live. Bit of a delay in stream. There we go. Okay, cool. Hello. Welcome back again to the stream. Last couple of weeks, we've been doing a little adventure game. It's been fun, a little distraction. What you need every once in a while in these trying times. I had a good week off, just to relax and chill out. But I started the old job hunt in earnest, which is super great. I'm just getting kicked off, having a good time. Oh, as good as you can have. Drop stunts make me a little nervous. It's okay though. It happens, everybody. We're going to stream today. We're going to code some Haskell. We're going to get back to the database. I think that's what people have been asking about. So let's get down to it. Last week, or last time we worked on the database, which was like 2 weeks ago. Well, maybe 3 now. Ooh, time flies. We started working on the database index. Provides us a lot of the key operations we need, like being able to look up keys, get keys, that sort of thing. I've been buzzing around a lot in my head in the past couple of weeks about this approach we've taken. Hey Ben, welcome back. Nice to see you. Nice to see you back. And thanks to also my new followers who followed in between streams. Super awesome. Every little follow helps. That's why I do this. Spread the love. Spread the love. Yeah, I've been toying around this approach in my head a lot in the last few weeks. So originally we started with the requirement for this key value data store that we wanted to keep our store. I think the only real major high level requirement we have is that the store should only take up as much memory as the user tells it that it's allowed to, with some affordance to the RTS in Haskell. So that's the garbage collector and some of the intermediate data structures we create and the server, the connections and things like that. Those all take a little bit of memory to run. So as long as you have enough buffer plus whatever you assign to us, that's all we're going to take up. And, we could do this with a hash map. Right, I've written toy little implementations of stuff like that before, of key value databases like that before, right? Since we're only doing get, put, update, and delete, you really could just do this with a hash map. So I was thinking, like, as long as we had a hash map that could fill in the requirement that it knows, or some other component of the system knows how much the data store itself, where the values are stored, takes up. We don't really need anything too complicated. So I thought, oh, maybe I jumped the gun a little bit on some of the complexity introducing this B+ tree. Why did I choose the B+ tree? Well, the idea with the B+ tree comes from databases and disks and things like that, loading things into memory. And I think it's still going to be a good approach here because, at least over a hash map, and a couple of reasons for that. The tree, right, a B+ tree especially, is all the data lives not in the tree technically, but at the leaves for one. And that means that the leaves can have, say, pointers into foreign memory, right, if we need to go down that way. In order to store, because the user might be, say, uploading, we might not bound the size of the values, and the user might be uploading, I don't know, a few hundred megabytes into a value, into the key value database. If they have a few terabytes assigned or a couple terabytes assigned, that would be perfectly fine. So one of the things that's going to get a little bit down the road, a little bit difficult with this design, or the reason why, sorry, this index is a good idea for this design, and having that at the leaf nodes at the bottom of the tree, is that if we have to marshal data across to C, or if we have to marshal it to a structure called a it's like fixed regions. It has a different name, but there's a data structure you can use in Haskell called a fixed region, which allows you to store data in it that the garbage collector will basically ignore. It'll be like kind of like an opaque pointer, and anything inside of it, it could be all kinds of objects, but the garbage collector will only see the one reference, which we might try experimenting with. But the cost of using those things is pretty high, so you don't want to be loading all that data in memory, like all of the entire store at once. So this tree kind of lets us lazily load those things in as they're requested. Okay, so tree it is. One thing that I've been working on a little bit between streams is this idea here with the siblings. Because my original approach with this was going to be to use a pattern called tying the knot to link these together. Because if you recall, a B plus tree structure sort of creates a linked list of all the leaf nodes at the very, very bottom. And boop. That means pointers, usually, in a lot of the other languages that have them. And Haskell has them too. But I didn't want to complicate our algorithm with that right now, even though we might end up in IO anyway. But each of these, so this maybe thing here, all right, so this little structure here is represented in our data structure by this. All right, so every time we split a leaf, which is kind of what we finished a few weeks ago, we would have to redo those links at the bottom, right? And we'd have to, if you can imagine a row of these, and we get the rightmost one, we're gonna have to, other than the last one, there's only one on the end. We're gonna have to redo the links and tie the knot for all the leaf nodes. Tie the knot into this one, and then that would finish it off. And since this is going to be a very sparse tree by design, with a very high branching factor, there's going to be the bottom of the tree is going to be really wide. And so there's going to be lots of those, and if we're going to do this in a pure fashion, it's just not going to be terribly efficient. So I've been kind of exploring around, trying to figure out if there's a different way we can encode this tree, or if we could relax some of the restrictions we've put on ourselves for this implementation. The reason why those pointers exist is so that you can do really fast iterations. So if you have pulled up a lot of these, say, fixed regions, or we've unmarshaled a lot of data from C, and we're pulling up these big blocks of data from in our leaves, and we want to iterate through a range of them, we could do that really fast without having to traverse the tree and all sorts of things like that. The other reason is that you can do range queries, but we're not really doing those. So I'm tempted to just throw this out. Maybe not the whole thing, but this part of the data structure, and sort of keep everything else. Just so that we don't have to start tacking IO onto everything, because in order to make this really efficient, we'd probably have to put IO refs here to some other node or some other leaf. KB. And once you have an IO ref in there, then our insert will have to have IO on here, and then it's just going to be not something fun to deal with right now. I'd like it to be pure, and since we're not really doing that linking together, since we're not doing range queries, and ultimately we're probably going to be running this data structure inside IO when we start getting into concurrent access to this thing. I feel like this is something we could tack on later, or we could revisit. So, thinking of getting rid of that. The other thing I was thinking about is this. So we've written split leaf. Right, this is one operation that we do when we're visiting a tree and building it and inserting a new node, right? This is a helper function used by insert. And we use it down here. I think that's about it, right? I don't quite have the Haskell tooling. There's a new version of GHC, a Haskell language server that came out. To get distracted for a second, and it just, I haven't quite got it working out with the crate. I added a Cradle file so that this would all work better, but anyway. Yeah, where was I? Right, split leaf. Yeah, we only really use that here. And look how big it is already. And I don't think this is gonna go away entirely. There's a couple of things we also have to do with split leaf too that I think we discovered was that one of the requirements for our B+ tree is that all of the nodes, all the keys are stored in order. And this is by construction, right? So if we start off with a key and we have an order of 3, a tree with an order 3, and we insert 5, say 4, and then we insert, that means we can have like up to 2 keys and we can have 3 children. All right, so we go to insert, say 5, we tack it on here, that's cool, right? Because 5 is greater than 4. So this is in order. All right, but say if we added 3 next. Right, 3 would be less than 4, so we would try to add it over here. But if we add it over here, right, we would break our invariant that no node or leaf can have more than order -1 keys. So we'd have a situation we could call like overflow or something like that. We have an overflow where you have too many nodes. So we got to split this apart, and that's where we're doing split leaf. That's why we're doing that, right? So we would add 3 try to add 3, but it would cause an overflow, so we'd have to split this up, and this operation would, at least in an order 3 case, would take 4, the mid one, as a parent. So we'd add 3 here, split 4 up, and make it a new parent. Right, and then the left and the right would be 5 and 3. Right? Or we have the case where we just say we wanted to add 6, right? We got to search first. 6 greater than 4. Yep. There's a child there. Can we go down it? Then we can add 6 over here. But actually, I'm thinking B trees. Sorry. Our split operation is a little bit different on a B+ tree because we do that, right? And that's because all the keys will be at the leafs levels as well. And normally they'd have like the little da-da-da, but we're going to ignore that. Right. Take that out. So the other thing I was thinking, and I mentioned this when we first started getting into this, is that maybe let's avoid doing any too much type level stuff. All right. and try to do everything at the term level. Now we have some types for our structure, but we're doing that a little bit when we get to keeping the order in our tree here. We have it in node order, we have it in leaf order. That means we're duplicating that value throughout our tree, which not the worst thing in the world, but that's a little bit of extra data in our index that's kind of redundant, that we're copying all over the place. And we do that because we need to know the order when we go to split and do other operations and things like that. So I'm a little bit concerned that this is going to get really noisy and loud. But insertion order, just to cap that off before we move on. The other property we need to make sure of is that like this is all in order here. So all of our trees and all of our nodes are all in the same order. Make sense? I hope so. I'm learning as I go. So I got to thinking. When we do this down here at the term level, we kind of have to we have a lot of let bindings. We have this if statement. We have, I feel like this is going to grow even more and just keep growing and growing and growing. And we're at a point where we're also going to have to start adding a fair number of tests to make sure that we actually implemented this correctly. So maintaining that invariant that we don't get any degenerate trees. So like our type definition technically currently can allow us to build trees that could look like this. There's nothing stopping it from doing that, other than us making sure we don't write the code that does that. And we won't be able to capture all the properties in the type system, but we could capture a couple. To follow along from the ideas in the last couple of streams I was doing with Haskell patterns and things like that, making those unrepresentable states unrepresentable, or illegal states unrepresentable, or however you want to say it. So I was thinking maybe let's give that a shot and see where it goes. And if we like it, we can take it and we can roll with it. And we can use what we've learned from implementing this split operation, which we'll still need, and see how it works. Okay. So I'm going to try a Gadet encoding of our tree, and that's what we're going to try and do today. That's the feeling I want to learn about. And see if we can encode the height invariant, and so that we don't get those degenerate trees by construction. I'd also like to be able to move the order out of our node and leaf types, and because that's really just metadata. And I'd like to create a type that we can expose to from our library here that kind of hides all that bookkeeping. So I want to make sure that that doesn't happen. Did I get disconnected? Sorry, I'm just noticing that I got welcome to chat message in my chat thing. Oh no, the connection's bad. Hopefully I'm going to bounce back in a second. My connection's a little bit funky right now. I'll just type in the chat here. Seems a bit jank. I don't know. I'm not terribly good at on Twitch and stuff. I'm not really sure if how to like switch servers and stuff like that. So if it gets terrible, I keep getting disconnected, let me know in chat. I'll try and figure it out together. Get a little distracted. Yeah, so I'd like to be able to do that. So we can hopefully have lean on the type system to help us design this a little bit easier and maintain some of these invariants for us. Okay, so where are we at on the branch, by the way? I think let's see, we added the HIE file. We started about 4 commits ago. We may end up squashing things down and cleaning up this branch, so it's not such a huge merge. But let's just plow ahead. Okay, let's take that out. Let's get rid of the leaf order here at this level. And let's do the same for node. Okay. Next thing we're going to do is we're basically going to start tracking the height of the tree at the type level. And we can do that by using a data structure that encodes numbers as a type, which we have int, but you'll see what I mean in a second. So we write it out like this. It's a recursive data structure. And if we enable an extension called data kinds, we can use the constructors to fill in types and lift them up to the type level. And what this would do for us is allow us to write functions where the leaves would be at, say, height 0, or at the bottom of the tree. We could write another function like when we do the split and we create a new parent, that the new parent has to be 1 higher, or the successor of a natural number, the prior level. And by using data kinds, we'll be able to, we can encode that in the types. And so when we write that function, we can't make the mistake of creating a degenerate tree. The type system will catch us and say, like, look, you were supposed to, the tree you gave me and the one I'm splitting is only supposed to be 1 level higher, that kind of thing. So it kind of forces us to be correct by construction. And then we need a different way of encoding B-tree node here, which would be using GADIT, a generalized algebraic data type. Okay. Super dope Haskell magic. Hopefully it's not going to be too cray-cray. I wouldn't want to upset my future maintainers with too much fanciness. But a little sprinkling, a little bring of fancy sometimes helps. I also think this data structure in general, after looking at it for so long, would be better expressed in a dependently typed language anyway. Okay, thanks, Camelon. Oh, Kamal. How you doing, friend? It's nice to meet you. Okay, so yeah, so we'll encode that stuff in our GADIT here. So I'll call that. I'll just comment this out for a second, or maybe I'll just get rid of it. Bang, gone. data tree. This will have, now I don't know how to fit the order in yet. It has our height, our key and our value type as parameters. And then where we can specialize those, the types of what these things are by our constructors in the normal gated way, which is going to come in handy. So we have a node. How do we construct a node? Well, we can give it a node of a key and a value, and it can return a B tree with the height information encoded in it. And the thing I was talking about before should be here. We should actually be saying this would be successor, which means we need to put kind of phantom type parameter up here in node, even though we don't use it in any of the types down here for in the product itself. That height information will be encoded along with the node as a phantom type, so at the type level. Kind of makes sense, I think. All right, so that we'll put back here, right? And this is what's letting us say that you'll give me a node, right? And I need to construct something one level successor, the higher of that. And then we have the B leaf. Right, the B leaf would just be basically a B tree who's at the 0 level. I think we'll need to tick these and data kinds just to show that they're, yeah. Okay. Slightly concerned because my IDE integration isn't. Is it telling me what's going on? No. Okay. I think the J4 is implied. Is it watch? File watch. And we actually want to do that in the server. So that's what we're working in right now. Cool. Yeah, that'll be type error. I know that one. That's fine. All right, so we have this B tree node. I kind of want to stick the order in here as well. But like if we pattern match on this gadget, we'll be able to pull that order out and use it. But it does mean we need, when we're constructing a B tree, you have to pass it in. All right, so we'd, or maybe we have to go like that. I don't know. I'll try and pop the order in later once we kind of got this going. See how it goes. See what the types say. Let's just, yeah. We can revert this, get this back, this code back if we don't like where we're going. So I'm just going to get rid of it. Pow. We're going to need it anyway, maybe at some point. Let's push it way down, out of the way. Okay. So this gadget encodes the idea that when we construct a B node, we give it this internal node and we can create a B tree whose height is the successor of that node's height. So if initially that's 1, then when we construct a B node, we can get a 2. And the leaves always start at the bottom, 0. I'm liking this so far. By the way, there's a great post on this from quite a while ago, where I'm drawing a lot of this from, that you might want to follow. I'll post it in chat at some point, probably near the end, and leave a link in the description of the video. But yeah, it kind of walks through this, but actually doing with just B trees though, but not with our kind of tree. So we're gonna have to take inspiration from that and kind of roll with it, and specialize it to our use case. So I'm learning some new patterns here, which is kind of cool. Right, so we got node, we got leaves. This B tree encodes the height information, that kind of meta information about our tree. And now we also don't want to expose this B tree directly. I don't know if there's a better name for this at the moment, but we can do the same thing here with another get and it returns a tree with just the key value types. And this would be what our main consumers of our library would use. Right, so they don't have to worry about instantiating it with a height and all that stuff. We're going to construct it to our functions that way and use these indicators along the way to help us with our implementation. But the users of the library, which we're going to be doing, don't really care so much. So this will be a way of basically removing that bookkeeping and kind of giving them back a tree. We can give them a constructed B tree or B plus tree, and they just get back a plain old tree from us. And maybe this should be like an internal tree thing, but we'll roll with it for now. It's cool. Yeah, so now our insert function, I'm going to comment this stuff out just so it doesn't get in our way. Our insert function is a little bit different now. Same idea though. No, we're going to need that exactly. But that's scope type parameters. Those are kind of there implicitly. So I might just add them if GHC barks at us. But we do need an ORD constraint on the key, because remember we need to keep all the keys in order when we're doing inserting, which is one of those things I think we missed when we worked on the split leaf, and we realized like, oh, if we need to insert these things in order, and we have the keys and values, oh yeah, that was the thing. The leaf keys and the leaf values in two separate vectors. When we sort the keys, we also need to move the values they're associated to as well. So we might need a function to do that kind of insertion into the leaves for us, or even into the nodes as well, because the keys need also associated with the that's not going to help at all, because it's probably got a whole bunch of hooks into my editor that do a bunch of things. Ugh. Okay. Second, I'm going to fix this and make this better so that we don't have to deal with this for now. And I'm going to fix my editor tooling this week. Yeah, get rid of that. Yeah, you can recar them if you want. That's fine. I'll get relaunch Emacs back there. Bang. Cool. Okay. We'll have to deal with our semi-okay Emacs integration for now. Sorter store. Okay, cool. So hopefully that'll show the type hole. Yeah. Yeah. B-tree node. Oh, yeah. Change that to B-tree. We can no longer derive equal and show for those. That's fine. Until we can derive them for or get it. Okay, so this is the whole. We got to produce a tree of K and V. I was kind of explicitly importing or putting the for all there, KV. But you can see it's implicitly there, inferred. Or K, constraint, we've got a key V, tree key V, tree key V, right? And what we have in scope, so we pattern matched on the tree there, we have our internal now. B tree with the height value, key, and the value, KV, which we've also have through the parameters. We have an insert function and blah, 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 blah. And our goal here is to build back up this tree. Okay. So this is the reason, one of the reasons why I wanted to go down this route and try this out and experiment with this. I thought it was a little bit better when I was playing around with it. Is that when we're writing this code with split leaf, it was it started to get a little procedural, a little, first we got to do this and then we got to do that kind of thing. And not very operational or algebraic, So when we're talking about splitting the tree, splitting a node, right? That's something I would like to capture that we're doing. So let's just go back to the drawing board for a second. So we got a tree that we have here. Let's say we have an order of 3 again. And we've got some values here. Got some values here. And we got some values here, right? So these are our keys. This would be a node, right? So this would be our keys here. That's what that relates to in the diagram. And these down here would be the children. You can imagine this as a list internally here, right? Our vector. Okay. We got to assert a new value, right? And for whatever sake, these are going to be like 3, 4. This will be 5, 6. This will be 5. This might not be quite right in terms of how this would be structured, but let's see if I can dip. All these insert operations came in, basically. So we can go here, 5, and then something else. And we could have another child over here. This makes sense. This does make sense. It's kind of fun. I was actually doing this with my daughter, who's only 7.5. I was trying to explain to her how this all works so that I could understand it. We haven't tried it before. It's pretty fun. Try to explain B-trees. Wow. Hey, Simon. How you doing? I haven't seen you in a little while. Simon, everybody, if you haven't chatted with him before. He's a pretty awesome person who taught me a lot about formal methods, who got me into Haskell in the first place. And yeah, it's an all-around awesome cat. So thanks for coming. I believe you're waving. I feel the wave vibes. It's good. Okay, so I'm going to try and like draw this across the way, right? So at stage 1, we start off with a leaf and we insert some value into it, say like 3, right? We're going to have a tree of order 3 for simplicity's sake. And then we add 4. What do we do? Right, well, there's room in our leaf node to add a 4, so we just kind of tack it on. It's greater than 3, so we add it on this side. And I'm just inserting here, quote unquote, inserting. Cool. So then I add, say, 2. Okay, how do I go about adding 2 here? Well, when we go to add a 2, we have a situation where we could try to like, or say 5. Let's just go to the right. So we have 3 and 4. We go to add 5, but this would violate our invariant that the number of nodes we can have, or the number of keys we can have in a leaf or a node is order minus 1. So we're only supposed to have 2 keys in here. And we can have up to, if this is a node, we can have up to three children, but this is a leaf. But, right. So we break the invariant that we can't have this many keys in our leaf. Okay, so each of these values, if this is a leaf, would also, so we gotta do something with this 5. Right? And in the B plus tree, right, we discovered the last time on the string we did the split leaf thing, right? We got to chop off these 2 here and here, right? And we got to make 4 a new parent. And then 3 and 5 become children. Right, so that's kind of like a splitting operation. So I move 4 up here. I get 3. Then I get 4, 5. Okay. Everything's still in order. Right? 3 is still less than 4, and so over on here, 4 and 5 are greater than or equal to, and they're over here. All the leaves, all the keys are at the leaves, and they're in order as well. And if we were to follow this from left to right, they would all be in order as well, which is good. So far, so good. So that's what we did. We created like a split operation. We found we had an overflow situation. We had 3. We started with 3 and 4. We pulled that 4 up as created a new parent. Created some new child trees, and that's that. And then as we grow this tree, there might become a situation where we need to, when we do that split operation, we need to attach it to an existing parent. All right, so if we did the same thing where we've got this tree now, and we try to add 6 over here, we get another overflow. Right, because first we search down here, can't go there, search through here, we'd have to go all the way over here. We got another overflow situation, we have to split again. We do the same thing. All right, and where we end up with 5, and we have 4, and we have 5, 6 over here. We still have the 4 floating over here, and we have 3 hanging out over here. And we have to do something with those as well. And so we'd merge 5 over here, and then we'd be back in balance again when all our invariants would be met. So we'd now have 4, 5. We have a child here in the middle, which would be 4. We'd have a child over here and over here. 3, 5, and 6. Then we're done. We still have 3, 4, 5, and 6, all the keys we've entered so far. We still have 4 and 5 here. and all our variants are still satisfied. Right? We can't have, we're at the limit of what we can have down here in this tree with children of this node. But I think we'll be, if we split again, we'd have to split this one, create a new root node, and then do that and keep spreading wider. And with higher factors, which is what we're going to end up using for a database, a real database, a production database, we end up getting these kind of really, really wide trees with a fair number of keys in here, and then like a really wide number of keys here. Right. So notice that when I was mentioning it, I was talking about like split, right? I had insert, I had split. These are like, when we're talking about just the parts of the trees and the parts of the things that we're doing, we're reusing split over and over again. We're reusing insert over and over again. These are kind of operations that we do. And as we recurse down the tree, we're going to be using these kinds of operations to construct those sub-branches of our trees and kind of merging things back together. And because I kicked out that requirement that the leaves are like linked together, like a linked list at the bottom of the tree, if we kick that out, then we don't have to worry about doing this all in IO with IO refs. We can keep this as a pure tree, which I think will satisfy most of our requirements for this project. So just something to note there, insert and split. I want to capture those operations, give them names, and then be able to reuse them. So as we're writing insert, back to the code. As we're writing insert, let's keep that in mind. The next thing we need to do is basically just write a little helper function. We've unwrapped our inner tree node here. So if we tried to write like an insert prime kind of thing with our tree, let's say our key and value. What do we get? What's the type of insert? Well, we don't have that yet, so let's just go define it. And we could just put a hole, I think. Yeah. And it'll infer what it thinks it is, which is not terribly helpful. So another thing you can do that I learned about from this handy video that somebody in the Slack, Chessa, I think, mentioned that this was kind of a trick that used to be used before we had type tools. But I still find it's actually kind of a neat thing. Sorry, not type of. Create like a dummy type. And you say this is undefined for now. Another way people used to do this kind of thing is to give a dummy type. And then you get this type error where we expected a function like this, but you gave us a foo, right? So we don't really care about that, but this is the type of the kind of the function we want, right? Except we're probably going to put our key and our value here. Right, cool. That's kind of what we want. Here, sort of. Except that, let's apply to 2 for your arguments. Huh. Something. Oh, wait, what am I doing here? I have to clean this up a little bit. Key value, that's right. Almost got it. It's probably just a paste error or something. Key value. Those should be the same as well. Yeah. Okay. So next thing, right? If we're going to write insert, we could just go from here. Just start implementing right away. But if we just stop and smell the roses for a second, we notice that the return type of our insert prime here is missing our h. Right? There's no height. So if we do this and we pattern match on our B tree, get it, and we implement it for node and leaf, and we return, and we have to wrap it back up in a tree, we're going to get into a place where we're losing that height information. And as we're recursing, that's going to become a bit of a problem, right? Because we're not going to be able to keep track of the height of the subparts all the way down, which is why we're doing it this way. So following along with this, it's kind of recommended that we do it this way, where we have like a return type. A return type of like our insert operation. And we have those two cases, right? We got insert and split, or since we're calling this the insert operation, well, we have two insertion things that we do. We either keep the node as is and we inserted the value. Sorry, so we just keep the node. Or we split it. So keep would have a what would it have? A B tree, right? Or we split. That would be an equal sign. Silly guy. Gah. Right, and we splitting. We have the B tree HKV, a key and a value. We're trying to insert, and another. Well, actually, we would have. What we would have? We would have. When we split, we'd have more than one. We'd have many. We'd have two. Yeah, two lists, two vectors of B trees. I think is the right thing that I'm looking for. All right, does this make sense? I think this is okay so far. Another vector of B trees, right? So we have two sublists of children that we're splitting apart, and the key and value that we're trying to insert. Actually, we might only even have the key. We're doing a split, right? Let me get a better color for that. Yellow might be good. I don't know if you like the yellow better. Let me know if you do. Right, but if we're splitting this node, and say this is like, it could be a node, it could be a leaf. It doesn't really matter how many children it has. Right, we're going to take the middle-ish one. Okay, so it might be this node in particular. But we're going to end up with that one becoming a new parent. And then these ones are going to become the two childs. But what we're going to end up with when we complete the split operation is going to be a node. Right, whether it's a leaf that we start with or another node type, right? And since our nodes don't carry values, I think all we need to have here is the k. The values go in at the leaf nodes at the bottom of the tree there. They could be pointers or whatever. So in that case, I think that makes sense, this type here. The way I've ordered the arguments, maybe not so much. But we're going to end back where I was. k. Yeah, we'll put the k over here. Yeah, we end up with 2 parts, 2 children. And we're going to return a B tree of that. And that's our 2 cases. So instead of returning a tree, here we return the result type, which will have the h in it, the height. Right, we have kind of another problem here. We're not returning an insert result to our users, so we gotta do something about that. Have like a little finalize function that converts it back to a tree. Right. Yeah. So that's fine and good and dandy, but finalize now is going to basically pattern match on the insert result types. So its type is insert HKV to tree of KV. Right, and so we can write it this way, where we have the keep case, which is going to be some node. And I think that could basically be just wrapped back up in our B node. Right, we're just keeping it. Oh, sorry, a tree. Oh, that should be a B tree node already. And the split case, where we have our key and the 2 sets of children that we've cut out, carved out, we split. Right. And again, our job here is to return a tree. And then we'd have to construct our node with this value. However we're going to do it. So we only have a key here. Probably have a background. That doesn't make quite a whole lot of sense. Right. I don't know if this makes a whole lot of sense for a split our K operation to just have the key, because we have to I feel like this should be somewhat similar to here, where we're just wrapping it back up our result in a tree. But, you know, all right, whatever. So we have a B node. It's going to be a node. It's going to have K, or be a from list of K. And children is going to be, what is it going to be? The vector join or whatever. If it has such an operation. Left, right. Basically, we're going to join together the 2. Or maybe we could just, no, those are going to be, yeah, those are 2 vectors. So I don't know what it's called. B concat vector dot something. It doesn't really matter too much. Maybe it's concat. Yeah, something like that. To match type, because it's 2 arguments. But it only has 1. I don't know. Anyway, maybe it's append. you get the gist of it. I'm just, the other thing here though, so the next step after this is basically recursing through the tree, and we're going to be calling finalize a lot to convert it back to a tree, pattern matching out the tree, passing it into insert prime here to construct the next part of the tree. And this could be a fair amount of work. So here's what I've been learning about in the past few days. And it's a vector plus plus. Yes, that's pretty much it. So I pretty much can do it like this. Parser, of course. Because I got to put it in braces or something silly like that, don't I? Anyways, yeah, fine. Okay, whatever. Put it at the beginning. Yeah, thanks. Thanks, Simon. Yeah, so the cool pattern here, this is fairly common in other programming languages, especially in the Lisp world, is this continuation passing style. So I was talking about this. Yeah, don't need the back quotes. Thanks. There's a slight delay for me in the chat. So apologies. It is what it is. Streaming. Massively multiplayer pair programming. Or in our case, not so massive, but that's cool too. So yeah, that could get pretty noisy here. So we can convert this to continuation passing style. And continuation passing style, I've been trying to think of a good way to explain it, or to introduce it. But the idea is that instead of finalize, kind of pattern matching on our result type and then constructing a tree and then passing it back, and then we have to pass that back into insert when we recurse on the subparts, unwrapping things, and so on and so forth, we can pass our operations in to our builder function. Okay, this is kind of the intuition I'm going with here, so bear with me. So if we consider insert prime our builder function, we could pass in continuations that tell insert prime how to build subparts of our tree as it's recursing, and insert prime can choose which continuation makes sense. Right? So if we're recursing on a node, there are certain choices we can make. We can split on it, right? Or we can just keep. Right? And if we go to a leaf, right, we can keep and split on that as well, but we don't have to thread through wrapping and unwrapping the tree type. We can just use with our internal representation. And we can convert basically insert into these keep and split operations into function types that insert prime can then call into as it needs to. And if we discover others along the way, then we can just add them in and do that. So it's called continuation passing style. And let's get to the code and you'll see what I mean, hopefully. So the first step here is to convert keep and split into function types. So I'm just going to create type aliases for keep, and it has to take all of our parameters, and it's basically going to be a function that takes, what is it, a tree? Sorry. Oh, brain fart. Gah, no. This operation here, yeah, something like this. Where it's going to return a tree. Yeah, so we have to pass in to do that the key value, and we return a B tree, a tree, and V. Right. We also would need. What else would we need to do this operation? We'd also need the node we're visiting as well, I think. And split would result in something similar. I think. No, keep, we just keep. And then split, we have some key. Vector tree of HK and V. Really two of them. And we return tree K and V. All right, these would be our function types. However, if we should try and plug those in, it's going to get a bit noisy. We can actually parameterize on our tree type. And from what I understand, this will polymorphic types kind of constrain our functions. Right? They limit what's possible and what we can do. And as we're recursing through our structure, we're going to be setting t to our tree type as we go. And hopefully that will be fairly useful to us as we go along. So we changed the type of insert prime to take our keep our type and our split operation. All right, okay, cool. And then insert prime is going to be a little bit upset with us here. So let's just look at the type error. All right, we expected an insert, whatever. So we can actually get rid of finalize. We don't need that at all. All right, so we have this part here, actual type is this. I don't know what the heck that is. No idea. That's okay, we can get rid of that by giving a function that takes these. Oh wait, insert. Why is insert still in there? Oh, because we still have the type. Right, so insert no longer a thing. This is still going to be back to tree v kv, I think. Yeah, that looks a little better. I think that makes a little more sense. So our insert prime now is complaining that we haven't given enough arguments because we expanded the thing of it. So we have to give it our initial continuations to kick things off. For keep, it should just be the constructor tree. And in the second case of split, we have to provide a function here for split, and then everything should be copacetti again. So we can, again, try to infer the type here. Split has to be a thing. Split is actually a function. It takes, yeah, right, we have that alias, right? So it takes a key, some vectors, let's call them left and right, and returns a tree. Yeah, I'm not feeling too good about that actually at the moment. There's something weird with that, fishy about it. Just having the key, the K, and left and right. Maybe my spidey senses are a little wrong on this one. Right. So I've got right, I've got left, which is a vector of our children, hopefully properly split. We actually haven't written any code yet to do that, but it's there. And we do have a key. So I guess we could just, we could construct our B node and our node with that. We have enough information there to do that. Right. Our node takes a vector of k. So as long as we construct a new vector with our key in it, and we do that vector operation where we plonk the split children back together into one vector of children, then should be good to go. Might want to split that into a helper function. This is starting to get a little bit long in the tooth. Heading over to the right. Or maybe create a smart constructor to put here. Yeah, why don't we do that? I like adding I like functions. So let's do that. Let's do that. Yeah, so we'll call that I don't know, node. Okay, we'll pass it left and right. Okay, we don't have that variable in scope. That would just look like this. Some ord k, some k, some vector of b tree of hkv, some vector of b tree hkv, and some b tree hkv. Yeah, we need a binding for that. I'll just get to in a second. Types line up, looking okay there. So let's key. Right. What would that be? That would just be a B node of a node of the from list, or V singleton, singleton. Okay. Oh, sorry, key. Pardon-moi. And the combined left and right. No, we said that. Ah. Aha. Let's see. Yes. Does this, what is this saying? This, are we doing something silly? We can't construct the infinite type. H is not a successor. So the height hasn't been increased from here. How did it infer that? Well, that's kind of the magic that's going on here behind the scenes, I guess. So let's just go back to our B node constructor. Right. We're creating a new node of a particular height, and what it's saying, I think here, is that the height of this node hasn't been increased. How do we increase it? Or do we need to increase it? Is this the wrong thing that we should be passing in here? This should just be a plain dumb constructor that actually should just return a node. Yeah. So I don't think we can do that here. Okay. Right. Yeah, we have to do that at some point, somehow, don't we? Okay. Can't do it there, but we can do it here. All right. So in our final split, if we have one, that's what our split function now is. And now we can basically give those continuations names here. So we have keep, split as functions now we can use in scope. Right, and if we look down here, what do we get? I think we sort of fixed the T there. Hopefully. That's my goal anyway. Although it still says B tree here. So the idea here is that when we have a B tree, a B node of, I'll say like B leaf. Do we need the parameters there? Parentheses? Yeah. What do we get? Right, we're still trying to insert a key and a value. Right, and then we have a couple of choices we can make at this level. We can either split the leaf nodes. We can call our split continuation, which could be fine, or we could keep it and just put it in. So I'll just leave that undefined for now. The other case we have is B node. We have some node n. I'll keep it split. Okay, cool. Right. So I can define some insert into node function. I'll just call inf into n. Can we give it? Yeah, what do we get here? We're going to need to provide a type here. I'm going to use my dummy type trick. I don't know why the hell is getting confused. Right, so take the key, a value, a node needs to return a tree. And basic, I think at this point, what do we have? We have the node itself, the key and the value we're trying to insert. And if we don't have room, because we inviolate, we get an overflow situation, we need to split, then we can call our split continuation with the key. We still need to insert the values somewhere. At some point there, but I think we can call our split, perhaps. That seems okay and pretty reasonable. By the way, I didn't put the music on today. This has been dead quiet. Let's put on some tunes for the last half hour or so. We're going to be doing this. Tunage. For some reason my headphones are not connecting the right thing because Bluetooth. Hopefully that'll work. Okay. No new followers yet. So, but again, Simon, you should follow me. It's only right and proper. But if you do follow me, you'll get notifications of the next time I'm streaming, and maybe we'll see you again. And who knows, people? If I could convince Simon to come on and stream with me, you'd be in for a treat. Let me tell you. Okay, so let's give I think that makes sense for the equation for insert. When we're trying to insert it to our node, we got the key, the value, the unwrapped node itself. Thank you for the follow, JC. Oh, Jared. I think it's Jared Evans. So thanks for the follow. Yeah, so we got to basically give our insert here that type. So I'm just going to do what I did before and kind of copy that over. I think that makes sense for that equation, and we'll have enough information in this function. Clean that up a bit. K1V, K1V1. There's something I'm missing here on this, though. Well, maybe it's on this. The height increasing thing. Because if we split, it should be higher. But if we keep it, it should be the same. P, and then I think we're going to need our quantification here so that I can provide that thing. I'm going to need scope type variables, and I need to add the other ones in as well. H, T, K, and V. We need ord on K. Okay, we're going to need, the other thing we're going to need on this as well will come up in a moment. So I'm going to just stack my arrows. Should I stack all of them? I think I'm just going to stack all of them. So the other thing I want to say about, I don't really know much about M and P yet, except I know as a human writing this that if we do, or it should be H, H. Anyways, if we do a split, the height should increase, right? And it should be an error if it's not increased by that operation. But I think we're getting this here. Yeah. So it doesn't know which type variable I'm talking about here, but it knows that one of them needs to be a successor. Right. And the trick I saw in the video, in the blog post on this style, introduced the idea of using dummies up here as well while we're working on this. And fixing them. Fixing them, basically, the type parameter. So keep M split P. See if that helps. Not really. Might not be doing it right. So I'm just going to go back out of that because it's silly. Anyways, there's some trick to it. When I post the video, you can watch, you can see for yourself, and then we can come back next week and have a little chuckle about it. Right, but basically over here, we're going to have ord K, and I forgot the syntax for this, but P is going to be like equivalent to the successor of whatever M is, or H. Having a bit of a parse error on the input here. I think I might need to put parentheses around it. Cypher, Simon is saying, with the size of insert, wouldn't I be better off making it into a separate function instead of a local definition? I think so. I think so. And I think we'll get there for sure. It's a good suggestion. Thanks, Simon. Yeah, I don't like the nesting of here so much. But we can fix that once I sort of know what I'm doing here. And also making sure that I'm not using anything that's like in the outer scope as well. I'm capturing all of the things. Okay. So it's still, I still haven't quite hit it yet. Do I still need M here? Is that the issue? So it's saying that H1, K1, N1, V1. This node here, right? Oh, the node we return back needs to be higher, the successor. I think that kind of makes sense, right? When we do the insert operation, when we choose that continuation, whatever node we get back from that needs to increase the height of the tree. So I think maybe I just got this a little bit off, right? I think that might be what is happening. So not, this might not be necessary up here. It might be on insert down here that I need to do, and I just have the type of insert wrong. So when we do the insert here, whatever continuation we get back, the height of that should be increased by 1. Up at insert prime, we are kind of delegating that out. I think that's probably the issue. Let's give that a shot. I think it's pretty much safe to leave these here in case I'm wrong. All right, HK, TPV, KV, HT, and P, and V. Okay, we're covered there, yeah. So insert. So the insert for the B node case is where we're going to call the continuation to either keep the node as is and just add the value, or we split this particular B node. And when we do the split, it's on the splitting when we want the node we get back to be the successor height. Yeah. So how do we say that here in the type system? I think what we want is we have some node M, so a certain height. We want to get back node P, a certain height. A successor height. And then we need to call the appropriate continuation with our constructed node, our properly constructed node. I think that bit of sense. So instead, if we pattern match on the node here, we pattern match on this node, and we check it out. And if we need to split, we call the split continuation to get the tree. Yeah. And you basically get rid of this here. Well, we're running a little bit low on time, unfortunately, friend. So this is going to be one of those kind of head-scratching moments, and I don't know. I don't like leaving undefines and inserts and things kind of like half thought out before I walk away. I'd like it to be able to compile before we go, but I don't think I'm going to figure this out in the next 10 minutes. And I usually like to leave 10 minutes at the end of the stream just to kind of reflect on where we're going with this, catch up on the project, see if we've got any pull requests or open new issues that we need to look at, things like that. So let's look at our to-do list. Let's say we got that one done. We have AGADD encoding. This part, the order in order insert operation for the nodes and leaves, I think we're still going to have to work on that one when we start implementing the code for actually doing the splits and the keeps. And we might need to write a little helper the utility library for working on that to do that. So what did we achieve with this encoding versus where we were going with what we had before? And is this a better, or do I feel like we're on a better path? You know, that's kind of the question I sort of look back on when I'm evaluating which way to go, which is the best approach. We haven't seen it yet, but we're getting close to where the type system is going to start paying for itself and all this extra work with the added complexity of these. First, the continuation passing style, and two, passing around this type level data in the height of the tree. We're just at the leaves of the nodes where we're actually going to start applying the splits and the keeps. And I think once we see that type error, that's going to be like a good moment, right? Because we're going to see that we can't, the type system is going to make sure that we can't get it wrong. Because what we'll have in scope is all that we can construct a value with, and we basically have to provide the proof to the type checker that we have. We can construct a value of that type with what we have in store. So I think that will take care of the invariant that we don't construct a degenerate B plus tree. So I'm feeling a little bit better about this this structure, this approach. As Simon says, and helpfully, yeah, there's going to be a lot of inline wares here, but we should split those out into helper functions, just so that we're not trailing our code all the way to the right in a giant pyramid of doom. But I don't think the stuff we wrote down here was entirely useless either. But I think it will allow us to, we should keep it around, because I think we still need to do this splitting of vectors. And basically, I think what we'll end up with is that this will be just a little bit more generic and won't be specialized to a particular branch of our recursion. And that's kind of like what the benefit of the continuation passing style is giving us as well. It's allowing us to kind of break down the individual steps that we need to take when we're recursing through a nested structure like this. So instead of recursing into a node and then having a bunch of procedural code where we go, okay, if this, then that, and right, and then go recurse again, we're kind of breaking those up into smaller chunks. And we're giving them names, operational names, and we're right now we've mostly just thought about this in terms of types. We haven't written a whole lot of term level code yet. So I'm feeling a little bit better about this approach, and I've learned a fair bit in doing this. So I promised that link on that blog post. So let me just try and find it for you. It's probably in my history. Yeah, B-trees with gadgets. So I've learned a lot from this post here about this approach with the gadgets and with the continuation passing style. Specifically, the thing that was kind of new to me was using this pattern here with the tree and being able to, by pattern matching out, we can remove our internal representation and give a more simple type back to the users of the library, this plain old tree KV, because they don't really care about the height and variance and all that stuff, but we can track it internally still. I think that's a really cool pattern, which you can learn about by watching this video and looking at the resulting code and stuff. I'll be forewarned though, as you can even see just from this opening screen, that there's a lot of single letter variable names that kind of moves pretty fast. So take a few reads at it, a few passes at it. And we're going to have to specialize. I'm trying to specialize like this kind of approach to our particular data structure, which is a little bit different than what this author here, Matthew Brecknell, was building way back when, in 2013 in Haskell. But we're going to have to specialize it to our B plus tree, which is slightly different in structure to this one. But yeah, I'm feeling good about this approach. So I think next week we should be able to wrap it up. And I might do some extra streaming sessions. Like right now, I've got a lot of free time on my hands, so I might do some more streaming during the week off my regular time on Tuesdays. So if you can only show up for Tuesday, that's fine. We'll catch you up if we work on this during the week. I might just work on the adventure game engine or whatever other random stuff. But yeah, I'll expect a few more streams, and we'll wrap it up here. I'll just put this as a work in progress commit on the branch. I won't need that. That was kind of my messing around test file. Okay, cool. I will just tag this kind of like with work in progress. I don't know, convention. I don't know if I'll use that later, but yeah, we're exploring encoding for tree type. We're decided to drop the leaf pointers for now. And maybe implement rim. I think that sums up kind of our session today. So let's commit that and push it up. Cool. Well, thank you for coming out and watching me, chill and just build a database. Pretty fun to do. I hope you had a good time, and I'll see you next week. Take it easy. May your monads always be free, and may your types always check. Have a good one. Happy hacking.